Microphone, helper. Mic.
Oh, the mic. Oh, okay.
Hi. Good afternoon, judges, ladies and gentlemen. My name is Yeow. I'm from the YPWLC Polytechnic, School of Applied Science, Diploma in Material Science. Okay, so the lecture for today will be on the fabrication and characterization of nano to micro scale electrospun polyaldehyde caprolactone, which is a biocompatible polymer. Okay, so what is tissue engineering? Tissue engineering is basically the man-made attempts to engineer live tissues or even organs from cells. So to me, there are basically four main components of tissue engineering. They mainly the scaffold to form the artificial framework of and to mimic the extracellular matrix. Next will be the cells. It can be either embryonic stem cells or even adult stem cells. And after it will be the growth factors to help to stimulate proliferation and cell differentiation. And then last but not least, the bioreactor is to mimic the in vivo human environment. So the last product will be the engineered tissue or organ. So the ideal properties of tissue engineering scaffold. Firstly, the mechanical properties has to suit the intended application. So and then after it has to have adequate porosity. And then next it has to be biocompatible so that it does not provoke the human immune system that can cause adverse reactions. Next will be non-toxic and biodegradable. Biodegradable suggests that the polymer will break down into the body and after it will be either reabsorbed or be excreted as waste. So the mechanism of electrospinning. So firstly, polymer solution, which is the combination of a polymer resin and a solvent. And then the solvent has to be of a dissolving solvent and a conducting solvent. So the polymer solution will be eluted out from the nozzle here, which will then be subjected to an electric field of any driving voltage, of which after elution, the solvent itself will evaporate from the polymer jet and then drying, in which the ions of the conducting solvent will then migrate to the surface of the polymer fiber, thus being stretched across and then being deposited onto the collector. So the advantages of electrospinning, firstly, is very simple. There are only very few process parameters that can be varied to produce different types of fibers of different scales, mainly from nano scale to micro scale. So no molds are required. Very little amount of polymer and solvent are used. Fabrication time is generally faster than other fabrication methods such as porogen leaching. And then it's versatile. The process parameters can be varied, and then there's the ease of creating multi-layered scaffolds without the need of removing the scaffold from the electrospinning setup itself. And then the process is precise and the results are repeatable. And last but not least, it's still relatively quick. So the objective of this lecture the objective of this project is to optimize the electrospinning process parameters such as the driving voltage, the flow rate, and as well as the polymer concentration, and to fabricate polymer scaffolds of 500 nanometer, 1 micrometer, and 1 to 3 micrometer. And then last but not least, we also have to characterize the scaffolds for their mechanical, thermal, and physical properties. So for the methods, this project employs a systematic approach whereby it was done in three phases. The first phase would be the preliminary phase, where the fibers will be spun on a glass slide for 5 seconds, which are to be viewed on an optical microscope for the determination of its formation and non-uniform fibers. So at the end of the preliminary phase, there are a total of 44 different sets of process parameters that have been explored. So out of 44, only 27 of them will then be used in the selection phase for the further determination of macro-sized bits. So in the selection phase, there will be 30 seconds of electrospinning, and after that, these images will then be viewed under the scanning electron microscope. So from here, after thorough selection, only three sets of process parameters from the initial 27 process parameters will then be selected for the bulk sample fabrication phase, which will be electrospun into 100 micrometer thick scaffold and with selective duration. And these 3 scaffolds will then be used for the characterization using these various test equipments and tests. So for the characterization method, there are basically 4: morphological, mechanical, thermal, and physical. For the morphological, the equipment that we use will be scanning electron microscope. For the mechanical testing, I use the microtester, thermal, DSC and TJ to determine its thermal properties, differential scanning calorimetry, and the thermal gravimetric analyzer. So for the physical testing, the test conducted was the ethanol immersion test. So these are the results of the optimized parameters. So these are the main three out of 44 samples, 14, 23, and 44. They both produce, sample 14 produced a fiber diameter of 1 micrometer, 23 produced a fiber diameter of 1.81 micrometer, and sample 44 produced a diameter of 0.52 micrometer. So this is the table of test results, which will be explained further in the slides. So as you can see, this is the assay images, sample 14, 23, and 44. They are all taken at a 500 times magnification. So as you can see, that there are no bits. There are no bits formation, and all fibers are uniformly formed. So this is the test result. The test results were studied. So the effect of flow rate on fiber diameter, as you can see, there is a positive correlation between increasing flow rate and increasing fiber diameter, which shows that the increase in flow rate is directly proportional to the increase in fiber diameter. Next will be the effect of polymer concentration on fiber diameter, which also the same shows a positive correlation, whereby the polymer concentration, the increase in polymer concentration is directly proportional to the increase in average fiber diameter. Next, the effect of driving voltage on fiber diameter. This is a very odd trend because with an increase in driving voltage, the fiber diameter initially decreases. So after a certain point, it starts to increase again as the driving voltage was further increased. Last but not least, the mechanical properties against the average fiber diameter, it showed an indirectly proportional relationship between the increase in average fiber diameter with a decrease in Young's modulus. So in conclusion, the electrospan BSL scaffolds with average fiber diameter of 500 nanometer, 1 micrometer, and 1 to 3 micrometer has been successfully fabricated, and the electrospinning process parameters has been optimized. So then the fiber diameter can be varied by varying the polymer concentration, driving voltage, and the flow rate of the electrospinning machine, and thus the thermal and mechanical properties of the scaffolds were also determined. So for the significant milestones, after this project they are done, it was basically continued by NTU. So the optimized electrospinning parameters were used to make the electrospan scaffold of the desirable average fiber diameter. The scaffold will be used as a muscular layer in a 3-layer scaffold intended to be used as a cardio patch. So one of the scaffolds that have been fabricated, the process parameters were then utilized to electrospan the muscle layer of the scaffold. So in vitro experiments showed promising results. And in 3 months' time, this cardiac patch that is developed by NTU School of Materials Science and Engineering will then take this cardiac patch for animal testing. So the potential benefits that this cardiac patch can be used to treat heart disease patients, especially those suffering from degenerative cardiac muscle syndrome. So the regeneration of cardiac tissue is done with the implantation of the patch without the need of going through a heart transplant. And then the polymer itself, PLCL, is a biodegradable polymer. So this suggests that there's not a need for secondary operation whereby the scaffold has to be taken out. Because PLCL, being a biodegradable polymer, after being implanted onto the heart, it will biodegrade over time. Then after that, it will break down, and then the leachables that are being leached out from this biomaterial will then either be absorbed by nearby cells or be excreted out as waste. And then there's also a potential commercialization opportunity of the cardiac patch. So I'd like to express my greatest gratitude to a few people, Ms. Song Sini and Ms. Janet Billy for their supervision and their knowledge imparted. And together with Dr. Wong Yishan and Professor Tan Lepo from NTU School of Materials Science and Engineering for their technical guidance and collaboration opportunity given. Thank you. Yes.
So not all the case. Well, what do you think is the reason that it's not the trend is
To be
yes.
in this shape.
Yeah.
Okay, because initially, when there's an increase in driving voltage, the fiber diameter will start to decrease due to an increase in electrostatic forces, which causes the fibers to be stretched even further. To be stretched even more, causing them to be thinner and thus their fiber diameter to reduce in heating. So after a certain point, where the driving voltage is increased further, there's an increase in fiber diameter. This is due to the increase in electrostatic forces, which instead of stretching the fibers, it starts to draw more polymer solutions from the nozzle itself, which means from the polymer solution itself, thus allowing the fiber diameter to be increased.
Are you trying to create the finest fiber you can fabricate?
No, we are not trying to create a finest fiber because
So what are you trying to optimize?
okay, we are trying to optimize the electro spinning technique and trying to figure out which are the different sets of process parameters that are able to fabricate fiber diameters of specific diameters, because based on Dr. Wong Xishan's research, she has found out that cells tend to prefer fiber diameters of less than 1 micrometer to adhere on instead of larger diameter. So we are trying to so my project itself is trying to collaborate with her to study the effects of cell adhesion onto a range of fiber diameters. But my part is only to optimize the electro spinning technique and to produce fiber scaffolds of 3 different diameters.
So you're aiming for a specific range of diameters?
Yes, correct.
Around a micron or so?
Between 500 nanometer to 3 micrometer.
Okay. And within that range, you don't really care much about what the properties are? Do you care what the properties are? Are you trying to optimize fiber diameter or optimize properties?
No, we are trying to optimize the electro spinning process parameters
To get a fiber diameter,
yes,
or to get a certain set of properties?
to get actually both, to get a certain size of fiber diameter and as well as to get a certain mechanical properties, because
You cannot get both. Once you get a diameter, you have to come with a set of properties, right?
yes, correct.
Yeah. So you have to
Have to give and
you have to be clear to tell us, are you giving more weight to the properties or to the physical dimension of the diameter? Which is more important?
I believe you will be the mechanical properties, because
So you're optimizing for properties.
yes,
Okay.
because mechanical properties itself is also important, especially on different types of applications. Like for example, bone tissues, they require higher mechanical properties, such as the compressive strength, because in a human body, bone has to be subjected to body weight, and then body weight itself its magnitude is quite great. But unlike in soft tissues, the mechanical properties does not have to be as strong as the bone, because for tissues such as the muscle tissues and blood vessels, they do not need that high. They do not need that high stiffness. If not, they are not able to perform their own intended functions, such as the blood vessels. They are not able to perform their peristaltic forces in order to facilitate blood flow.